We have seen that recurrent neural networks are a powerful family of models that are able to process sequences of arbitrary length. And it has long been believed that recurrent models are the only type of models capable of doing that. But recently it has been demonstrated that there is actually a class of feed-forward neural networks that are able to achieve performance on par or even surpassing the performance of recurrent neural networks. And these are so-called autoregressive models that we will discuss in this last short unit of this lecture. What is an autoregressive model? A K-order autoregressive model is a feed-forward model which predicts the next variable xt in the time series, where again t indicates time, based on the k previous variables, xt minus 1, xt minus 2, and so forth. In this example here, in this graphical illustration, we have x5 depending directly on x4 and x3. So k would be 2 in this case. Note that I've used dash lines here just to indicate more clearly the different mappings, what belongs together, but the dashed and the solid arrows are actually the same. It's just to better separate the different mappings. Again, as in RNNs, the parameters are shared across time, which means we apply the same function at each time step t. The function does not depend on a time step index t or the parameters of that function. In other words, as in RNNs, the weight matrices don't depend on a time step t. They are shared across time. As we can see from this illustration here, if we think about this as a graphical model, we make a strong conditional independence assumption here now. For example, x5 is conditionally independent of x2 given x3 and x4. This is different from RNNs, and we'll have a look at this again in a few slides. Now, with a little abuse of terminology, we can extend this concept of autoregressive models that predict their next own value to the situation that we have been looking at for sequence modeling, where the outputs and the inputs are different. In this case, we have now the inputs in green and the predictions, the outputs in y, and we have a function or the prediction at time t depending on the inputs at time t and t minus 1 and t minus 2 all the way until k. So in other words, yt is dependent on xi, where I is bigger or equal than t minus k and smaller or equal than t. And it is independent of all xi's where I is smaller than t minus k. In this example here, y5 is independent of x2 or x1. Now, this is the most basic form of such an autoregressive model. We can see it's a pure feed-forward model. There is no hidden state that gets recursively updated. Here we compare the autoregressive model to the unrolled version of the recurrent neural network. In contrast to the autoregressive model, recurrent models summarize previous information through their hidden state, while in the autoregressive case, we have a direct connection from previous time steps to the current prediction, but only until a certain k. So we are clipping information. We are completely ignoring information from the past. We have this hard constraint here, while for a recurrent neural network, in theory, information from very early on can be remembered for predictions very late. So in other words, in contrast to autoregressive models, which do not have an infinite memory, which make this hard conditional independence assumption, RNNs don't do this, and they, in theory, have infinite memory. But of course, the question is, how valuable is that? And that's what we're going to have a look at in this unit. In In contrast to recurrent neural networks that require backpropagation through time, which has all the problems associated to it, as we have seen in the previous unit, autoregressive models are much easier to train, as we don't require backpropagation through time. It's a standard feed-forward model where we have standard supervised learning problems. We have them even independent for, in this case, y5, y4, and y3. We can just apply this learning in parallel and update the weights here of this shared weight matrices in parallel. So autoregressive networks are easier to train, they're more stable to train than recurrent neural networks, which require this backpropagation through time. Autoregressive models like RNNs can be extended to deep versions with multiple layers by simply stacking layers of this autoregressive nature, where we now have these are two different functions. Again, parameters are shared across time, but now in the layer direction they are different. So we have one function that maps from x to h, and then one function that maps from this hidden layer to the prediction layer y. What we can also see is that these autoregressive models effectively perform multiple causal temporal convolutions. Because we have shared parameters across time, each of these layers can be thought of as a 1D convolutional layer, where we swipe a kernel filter matrix here on this layer in order to produce the outputs. And they are causal in this case, in this particular case here, because we're only considering for making a prediction at time t information at time t and at previous time steps, but not at future time steps. Depending on the situation, you might want to consider causal or non-causal structures. If you want to process an entire batch, an entire sentence, where you don't have these online requirements, you might want to also consider information from the future. So you can add this information. Similarly, in recurrent neural networks, there's something called bidirectional RNNs, which also go left and right and left. So also take into account information from the future. But for the scope of this lecture here, we're going to consider RNN in the standard setting, which is the causal setting, where we're just taking information from the past in order to make a prediction. Of course, these type of models can be now combined with all tricks that we have developed, the community has developed in standard deep neural networks, such as residual connections across layers, and also dilated convolutions in order to increase the receptive field size much more rapidly while keeping the parameters the same. The first model of that type that was really successful and was demonstrating a breakthrough was from Ord et al. Called WaveNet in 2016. This was a model that was a generative model for raw audio waveforms, which generates realistic speech that is hard to distinguish from real speech for a human observer. It combines residual and skip connections with dilated convolutions, as you can see here, which is really important to consider context, to consider input information from many previous time steps. And this is important for audio. Audio is hard in a sense because we have so many samples per second, such that typically raw audio waveforms are avoided in the RNN, in the sequence processing community. Now here it has been demonstrated that not even with an RNN, but with a feed-forward network, it's possible to produce raw audio waveforms using these ideas of dilated convolutions, where we can, with few parameters, very quickly extend the receptive field size, and with this idea of deep multi-layer architectures with residual and skip connections. So this was really a breakthrough in the generation of raw audio waveforms, which is notoriously hard for sequence processing models due to their structure at multiple scales. There's structure at micro scale, at millisecond scale, and structure repetitive patterns at second scale. So it's hard to capture this structure at these multiple time scales. And this has been done very well by this type of model, and also demonstrated in terms of quantitative performance. These are measures of how natural speech is, and WaveNet has demonstrated performance far better than an LSTM, rivaling natural speech by humans. And then this idea has been taken further in this paper here by Bai et al. 2018, where we have demonstrated that a simpler architecture that uses the same ideas, deep multi-layer networks with residual layers and dilated convolutions and zero padding for information or for connections that range outside the input domain here. But otherwise, very standard network have demonstrated very good performance across different tasks. So here are several different tasks, from image processing, adding, copying, music processing, natural language processing, and across a whole variety of these tasks that have been considered the home turf of LSTMs and GRUs and RNNs. They have demonstrated that these very simple and easy to train feed-forward networks can actually outperform these recurrent models. And now, of course, the question is, why is that the case? Are these recurrent networks needed? Are they actually utilizing their theoretical advantage of infinite memory? And this is still a topic, an open topic for discussion. And I want to point you to this website here, which is a nice blog post centered around this topic. And here are some quotes from recent papers that have investigated that problem. Dauphin has in 2016 found that the unlimited context offered by recurrent models is not strictly necessary for language modeling. For instance, models that explicitly truncate the input sequence length at 13 or 25 are often competitive with models that have infinite memory, which indicates that maybe in theory the models with infinite memory are better, but in practice they don't utilize infinite memory, or for these particular tasks infinite memory is not necessary. This has also been observed by Bai et al. In 2018. They say the infinite memory advantage of RNNs is largely absent in practice, even when considering a variety of different models and tasks. So seems like these temporal convolutions are a real alternative to recurrent networks in many situations. And Miller in 2018 provided a theoretical result which showed that if the recurrent model is stable, meaning the gradients cannot explode, which is a property that of course we always want when training recurrent models, then the model can be well approximated by a feed-forward network for the purpose of both inference and training. So there seems to be also theoretical evidence for the fact that the theoretical advantage of recurrent neural networks of infinite memory is actually not present in practice. I want to close with this discussion, and it's a good starting point to think more about this problem and read more upon this. Thanks.